Yeah, thank you very much, and it's a pleasure to start the afternoon and also somehow the series. I mean, we had a little exercise session in December to test this WebEx setup, and it worked reasonably well. And so we thought we can move forward with this. And thank you also for the group who selected the abstracts for this session, which was not, I was not part of that, of course. And so I want to take the upcoming 15 minutes. It will not be a very long talk. We try to get the 5 talks within the 2 hours. To talk a little bit about feature data assimilation, we'll touch theories and algorithms and examples in a moment. And I chose to, I will not do a literature review on all variants of it, but I selected 5 topics to show you a little bit, which I think is like an appetizer, that it's a very interesting area. I've been looking into this over the past month and years. And this is a joint work with some people in my group. Christian Welzbacher has been in my group for a while. Now it's still in my group because I moved up, but in another part of DWD. And of course, and then we have some collaboration with colleagues from Japan on the topic for radar data assimilation and feature data assimilation. And I'll mention this again a little later. So let me show you. So, oops, now I have to here. First of all, at DWD, we run global models, we run European scale models, and we run convective scale models. And here I show you the setup of the convective scale model icon D2. The D2 stands for basically 2 kilometer resolution. And we are about to move this model to operations in DWD. And you see here the area, also some orography. You have the Alps included here. It goes from the Mediterranean to Britain and Denmark, covers this area. And we also plan to go to a 1 kilometer nest in the future, but that's not the current state. And we are about to go to operations very soon, 3 or 4 weeks from now. And so all the research on features some research on features has been done within this model. And over Germany, we have a radar network of C-band Doppler radar systems. So there are 17 of such systems. They all 16 of them are polarimetric, so they measure moments as well of the reflections. We measure reflectivity, radial winds, and these polarimetric moments. And they have a temporal resolution of 5 minutes. So they do a full volume scan. I'll show you the scan in a moment, every 5 minutes. They have a 1 kilometer resolution radially and 180 kilometers coverage in all directions. So basically you get disks of nearly 400 kilometers diameter, and then you have some angle resolution and 10 elevations basically covering the height. And here on the next slide, I show you the different scan pattern basically in the vertical. So here you see what is, there's some German on it, I'm sorry for that. So there's a precipitation scan, it's the lowest angle, and then you have higher angles and some very high angles, which of course do not completely cover the space, but a good part of it. And there is a scan pattern. You start with medium and then go down and then take the highest, and every 5 minutes you repeat this. So the point here is that basically, first of all, every 5 minutes we have a lot of data, kilometer scale resolution, and we observe convective processes in a high temporal and spatial resolution. And we want to use these for initializing our model and doing data assimilation. And we have been working on this for quite a while. So we are running the LATKF, the localized ensemble transform Kalman filter, as an operational system for our convective scale model. It's called KENDA, kilometer scale ensemble data assimilation. And we are now operationally assimilating 3D volume radar data within the model. And here you see some scores for the upcoming model. So at the moment we have Cosmo model running operationally, and we move to Icon D2 soon. So and here you see, if you look at, for a moment, just take time to look at this, because it's a background of the features I want to show you in a moment. So here you have the score improvements, switching data, radar data on and off, and their influence on the different variables of your model here, wind direction and wind speed, the surface pressure, relative humidity, temperature, and dew point. And you always see our whole domain and the German part of it here in the two columns, and you see lead times from 0 to 24. This is 1 day of forecast here evaluated. And green means with radar data you get an improvement, and here you see the scale is up to 5% in these variables. And of course, by your ensemble data assimilation, you have correlations within your forecast ensemble, and you basically map your innovations from radar space into your variables, your atmospheric variables, and you see improvements here. And on the right hand side, you see the skill scores, the fraction skill scores to measure the reflectivity forecast and the precipitation forecast. So basically you can calculate both and of course compare, but basically the behavior is very similar. So here you also see that if we have latent heat nudging as well as a technique to assimilate the precipitation scan, and then we have the LATKF on top of this to assimilate all the various elevations of our volume scan here. And you see over 24 hours is the time axis here, the improvement of if you switch on radial winds and radial winds plus reflectivity in terms of the precipitation fraction skill score. So this is classical radar data assimilation, and also what we do here is basically we use only the final volume scan of the radar. So we have a 60-minute assimilation cycle on the convective scale, and we only use the 60-minute radar scan at the moment for the volume radar assimilation. We also tested more, but we see if we take earlier data in a just classical 4D LATKF fashion, then this doesn't help us very much, because the data are older, and it seems that the newer data are more helping us to get better forecasts at the moment. And so we have been looking into this whole problem of high temporal evolution of the precipitation areas here, and the idea came up that basically, and it's an old idea, of course, that somehow you have to take care of higher temporal processes within your slower data assimilation cycle. And of course, you can use something like 4D VAR, which for some reasons we don't want to run on the convective scale. And the 4D version of the LATKF is one of the options to take care of the high temporal resolution of processes. And I will come to this topic again and again now on the next slides. But a second idea is that you use old ideas also from radar data assimilation, that you use transforms of your data or functions of your data, characterizing your data, and assimilate these functions. And that is what I basically understand as feature data assimilation. You try to observe particular features of your data. For example, if you have a convective cell, the cell size, the cell area, or things like this, and you can try to assimilate these cell properties or their cell features or their behavior over time within your data assimilation cycle. And my topic now will be to investigate this further. And the first thing is, if you have, for example, various cells in your model area, and then you simulate these cells 40 times, we have 40 ensemble members here for our LATKF, then different members will have cells in different areas. So how do you compare them? How do you compare properties of these cells in your data assimilation cycle. By the way, I have here just these images are just indicating our different processes we have. And in principle, you can ask this question for each process you can observe by some observation. So it applies to radar data assimilation. It also applies to satellite data and other types of data which you have on a high temporal scale. So one point here is you need a proper metric in your space to be able to assimilate these features. And after a lot of different trials we did over a longer period of time, really several years, we ended up with a very easy solution because we measure our precipitation in terms of fractional skill scores. And so the basic idea here is to use these fractional skill scores metric here to measure the distance between different phenomena in your ensemble members and your observations. So fractional skill score, this sketch here tries to explain this. So left you have some observations, right you have some model, and the model shows some phenomenon, and I indicate this. This is the graphics Christian Welzbacher. Here you indicate some phenomenon, for example, precipitation above 1 millimeter. So here you have this, and now you take a point and you count the number of features or the number of events in a particular radius. And you take this number and divide by the total number of possibilities, and the same for the model and the observations. And then you have a number you can compare, and it's basically a part of the fractional skill scores. For the score, you sum them all up, but here you take them point by point over your domain, and then you can do an assimilation. You calculate this for all ensemble members, and you feed it into the standard elliptica F. I didn't show the elliptica F here again because I somehow assume you know its formulation. If you don't, you have to look it up, but in principle, you can feed it into the system. So here's a result on our real world system. This was done with Cosmo, actually, with the still active model. So here it's an average activity above threshold is our feature. We use a 3D data reflectivity here as a nice case where we compare it easily to the standard data assimilation. We used a threshold of 30 dBz and a grid box size of 7 by 7 grid points. And then we did basically here 2 weeks of full feature data assimilation for some times, 6-hour forecast. You see here 6 hours. And what is interesting here, now we compare these feature only reflectivity data assimilation to the full volume reflectivity data assimilation. And if we assimilate with a 30 dBz threshold, then we basically feed in information now with the features of a 30 dBz. And if you look at a 30 dBz fractional skill score result, you basically see that we come very close with this feature data assimilation, the FSS data assimilation, to the full 3D reflectivity data assimilation fractional skill score, but only for 30 dBz. If you look at 20 dBz, for example, you end up with a smaller one. And now you can compare this basically for a lot of cases, and you see that, of course, what you feed in, you get, but also in the forecast as a real data assimilation. So that's my first point. You're choosing a nice metric, and the FSS metric here is very useful. And it really works, and it is comparable in the quality to full assimilation if you look at the right scores which you assimilate. So now we went further on. So now the question is, what type of features are useful? What do you do at all for feature data assimilation, and what's the theory behind it? And so here I now go for the rest of the talk, like 10 minutes. I go into some simpler cases. So I take a Lorentz model, Lorentz 63, as a study object, and I also used an oscillator model and basically verified the phenomena for both sides. So here I show you the setup and also some idea of another feature. So here you have your function as a truth in dashed line here. You have a model system. I change the model system from the truth, it's a nature run. and I do my assimilation cycle here. You see analysis times, these straight lines, vertical lines here indicate the analysis times. And then I also use now measurements. I use always a measurement at the analysis time and also some earlier measurements to have this temporal resolution of a higher order process. And here I call it YKJ, and the J goes 1, 2, 3. I'll stop with 3 for this talk. And I basically count backward in time here with the 1, 2, 3, because the 1 is always the analysis time, and then the 2 is this one here. So, and now I can calculate. The idea is what type of features can I calculate from these data, and I basically started to look at everything I could find. Show you 3 or 4 different things now and the results. So basically, for example, here, one feature I would call nowcasted field. So I take the 2 observations and I basically follow the line through the 2 observations into the future. Show you the formula on the next slide. And I can do this every time at analysis time. I use the 2 observations I have go into the future, and then I can assimilate future observations. I can do the same thing for all my ensemble members. I can do it for the real observation. I can feed them all into the LTKF, do an assimilation and see what's the score, how the score evolves. And I have a free parameter here, and that is the lead time of the nowcast. So I can go into the future, and if you do this, basically you get a weight for this difference here, which I call gamma. Gamma is something like the lead time divided by the time between the 2 observations. So let me show you this. So here's the same for the Lorentz model now. If you look at the picture for a moment, you see the classical Lorentz with all the standard choices for the parameters. And also you see some nowcasting here. You see the straight lines all the time. And somehow here I used a third of the assimilation cycle time frequency, basically, of the time distance for nowcasting. But I changed this and call it gamma, and I can move gamma from 0 to 10 or something like this, which is about 2 times 2 hours for our hourly assimilation cycle. So now you see Y1, Y2, Y3 counting backward in time for each assimilation interval. I use the nowcasted observation here by Y2 plus Y1 minus Y2 times gamma, but I can also go to higher order, like Taylor development of the observations in time, and also using the Taylor curve into the future, extrapolating the curve. And this is here Taylor with 3 observations, the formula Y2 plus Y1 minus Y2. So you have a linear term here, and then you have a quadratic term with the 3 observations involved. Classical finite difference way to estimate the derivatives here. So my third example I tested is Fourier features. So basically you can take for each of the observations, you have an observation vector. I call the component EI here, and YK1, YK2, etc. is the temporal evolution going backwards in time through your assimilation window. And you get basically an array for each component of the observation over time. And now you can do a Fourier analysis of this array, and using so sines and cosines, or the complex exponential here over time with time interval tjk and some order psi going from minus capital N to capital N. You basically do Fourier analysis, and this is written here. The Fourier coefficients are given by a matrix application. So before I go and show you and finish by showing you some of the results and then go into a discussion, what do you have to do with your observation error matrix and your priors? So first of all, if you do a linear transform, and all I showed you so far was linear transforms, and you should start with linear before you go to more complex things. So if you look at the observation error matrix for transformed observation, there's a classical simple derivation. You take the expectation of y minus the average, here ay or y bar if it's just y, transpose, and you get the R observation error covariance matrix. And if you pull this out, basically you see that the RF, so the transformed feature covariance matrix, would be the linear or quadratic transform basically here of the standard covariance matrix for your observation Y. There's one point. If you do this linear transforms in your LATKF, so you have to transform the matrix R, but you also have to transform your observations. If you build this all in, what happens is that basically the A here goes to an A power minus 1 here, and the H transpose on the other side goes to the H transpose power minus 1 here, and they cancel. So within your standard LATKF, and you can write down here the square root filter, or you can write down the mean updated. It just doesn't matter. All formulas show the same phenomenon, that basically if you transform all your observation variables plus the R in the same way, that cancels out and you get the classical 4D type update. So that will not change anything if you don't do this. But you also have to take into account your prior. And the question is, of course, if you go into the future and you want to assimilate future observations or nowcasted or predicted observations, you should also adapt your prior accordingly to what you do. That's will be a big discussion point, I believe. But if you would do this, then, for example, here the nowcasted observation is gamma x1 plus 1 minus gamma x2, and if you look at the variance of this, it goes up like gamma square plus 1 minus gamma square as a factor. And if you now build this in, it will cancel any factor in the R matrix, which is basically the same if you do the same process. And then you end up with having as well a B changed, and the game is open from my point of view to discuss what is the correct prior you should really use. And now I want to show you some results here. I want to end with 2 slides on the results and discuss them a little carefully. So I take 2-3 minutes for this. So here's the curve. The axis is the lead time of the weight factor. So that's basically the lead time for the nowcasting here, or for the Taylor evolution, or even it's a weight factor for Fourier I also used. If you set the weight factor to 0, you have the 4D version with 2 observations here for the nowcasting. If you set it to 1, you have a 3D version, but 2 observations instead of 1 at the same point in time. And then if you go further on, you have basically different ways of nowcasting. And here you see always the root mean square error. It's an average root mean square error over 100 assimilation cycles. So it's relatively stable. There's only 1-2% of change if you pick a different seed. And I show you the EB score, so XB minus X true, so the first guess at the next assimilation time, and also the analysis score at the assimilation time. And you see basically that with the nowcasting here, using the prior transform and the R transform and the observation error transform, the error goes down until factors gamma is 7. And gamma is 7 here is basically exactly the time where I measure the observation. So it's optimal for exactly my assimilation cycle frequency. And the same is for Taylor, actually. 6 is Taylor because it depends on where you start this. Taylor is or 7 here. So this worked very well, actually, and surprising for Taylor. I have to mention for you, I used a different nature run system than the data assimilate, the model system for the data assimilate. I changed some parameters. That's important. If you keep all parameters the same, this basically goes into noise. But if you go to a real world situation where you have differences, then this seems to work and really have a benefit. Here's the Fourier assimilation. So again, Fourier, this is the weight of the Fourier coefficients. And I also used, on top of the Fourier coefficients, just the classical 3D type of data additionally to also for the other 2. And here is my just testing the equivalence. So I didn't change the B here, but just the R's, and then basically for all weight times, I get more or less the same, up to some fluctuations from the random draws. And finally, here are some scores on this. So I show you my 3D, so taking just one observation per cycle is the reference. If I take 2, so over time, minus 10 minutes and 0, I get an improvement of 2% here if I take 3 observations for these Lorentz type systems, and the oscillator basically gives you similar results, minus 2.37%. The nowcasting had an improvement here for the first guess scores, of course, of 12%, the Taylor of 23%. The equivalence basically should be the same as the 2D or 3D, the 4D version for all of them, and that is the case. And then if I take only nowcasting without the 3D additional observation, I get 10% improvement to the 3D compared to the 3D, and Fourier features 16. Anyway, it was very interesting to me to observe all of this, and I've written it up in the paper coming hopefully at some point in the near future. And so that was my little appetizer on feature data assimilation, looking into 3D volume radar features or derived features of them. Here, looking at the fraction skill score, the oscillator model and Lorentz. I showed you Lorentz results, and I compared 3D, 4D LTKF with 3D plus nowcasting data, 3D plus Taylor data, and 3D plus Fourier features. And I also showed you how it's equivalent if you don't adapt all your priors and observation error covariances in an appropriate way. Okay, thank you very much. That was my contribution.
Okay, so thank you, Roland. We have 2 questions. Hopefully they can be answered quickly because we're a little bit behind schedule at the moment. Yeah. So the first one is from Peter Yan. Roland, how do you determine the observational error for the features, e.g. FSS? Question mark.
So what I did basically is, first of all, if it's a transform, I use the transform. If I look at the Fourier features, I basically look at the statistics of the monitoring and basically use O minus B type of statistics. I mean, so that's all you can, all what is known to do this usually can be done. You just have to apply it to these features. You can use de Rosier type estimates people do. I know all the complications with this, but I think here I basically chose something of the right order of size after observing it. So I must say it's important. Otherwise, you have a complete imbalance of the different observations. So you have to take that into account.
Okay, cool. And the second question is from Juan Wang. Are features defined by different thresholds, assimilated simultaneously, or only feature corresponding with one threshold is assimilated?
Yeah, so for the experiment I showed you with the radar, we used one threshold only. But of course, you would not do this. I mean, like for Fourier coefficients, you take several Fourier coefficients, like I did here. You would take different thresholds and use them simultaneously. We have not completely tested this. We have programmed a little bit, but this is ongoing work in our full system. But I believe that in principle, of course, you should use different features and different thresholds in the end. And that's a lot of work to test it and to see what makes sense. It's like a discretization a little bit.
Okay, well, thank you very much for that very, very interesting talk. We do now have to move along, and in theory, have